In this class, we're going to consider the power rule for integration. So like the power rule for differentiation, this is your primary rule. So at least initially, this is a rule you're going to use most often. And in fact, there's quite a lot of similarities between the power rule for differentiation and the power rule for integration. So we've already said that differentiation and integration are opposite inverse operations, and that's going to get reflected in how we go about the power rule. But the power rule you should give particular attention to. Like I say, it is initially the rule you're going to use most often. As you go further through the series, you're going to learn other rules, and you're going to start to use those. But at first, you'll just be using a lot of power rule. And in fact, you'll still use power rule even when you learn those other techniques. So what is, first of all, the format that we can use the power rule on? Well, it's just the same as derivatives. We're looking for functions that are basically in the form ax to the n. So you can see that all of these functions are in this form in some way or other. So there's no restriction on what the n can be. It can be a negative number, it can be a positive number, it can be a fraction. Fractions can be quite awkward to work with. You'll see that as you move through. In fact, I might even change one of these to a fraction just to, mix it up a little. Yeah, let's maybe make that like a 2/3 or something like that. So it doesn't really matter what the n is. Same with the a. The a can be negative, positive, it can be a whole number, it could be a fraction, it could theoretically be a decimal. Quite often, in fact, they're going to be fractions. And if you've got different combinations, like a fraction here and a fraction here, just like with the power rule for differentiation, it can be quite awkward to work out the numbers, probably more so in integration, because as you'll see, there's a division involved. And anytime you're dividing, either dividing a fraction or dividing by a fraction, things are just a little more difficult. So that's the format you're looking for. If you don't have this format, then you cannot use the power rule. So for example, one of the next rules we're going to look at will be the chain rule. So the chain rule might be presented in this sort of format, which would be essentially a composite function. You've got an internal function here, and then this overall kind of exponential type function. That would be an example where in differentiation you would use the chain rule, and in integration you're going to use a version of the chain rule as well. But that is not in the format to use the power rule. So if you see something like this, you'll know that you cannot use the power rule on it. So taking the power rule format, so that is going to be the integral of ax to the power of n dx. So again, just going back to our notation from the previous class, this says take the integral of the function ax to the n with respect to x. So how does the power rule work? Well, because integration is literally the opposite, the inverse operation of differentiation, that should be reflected in the rule. And if you think back to the power rule for differentiation, it says multiply by the power and then reduce the power by 1. For integration, it's both the opposite of those operations and the opposite order. So we increase the power by 1, first of all, and then we divide by the new power. So if you think about increasing the power of 1, then by 1, then that goes up to n plus 1. Okay, so we've just increased that n power by 1. Of course, this is in general terms. We're going to look at actual examples in a moment. Increase the power by 1, and then you divide by that new power, which is n plus 1. That is your integral. Okay, and you need, as we've already started to touch on in previous classes, you need to add on this plus c. Okay, so just to make this a little more formal at this point, this is called the constant of integration. And there are types of integrals we're going to look at later where you don't need this constant of integration. They're called definite integrals, and it's a slightly different thing. But for these initial integrals, and even when you start to use other rules like the chain rule or the trig function rules or a bunch of other rules you're going to learn, if it's an indefinite integral, which is the type that we're looking at the moment, and I'll explain that more fully in another class, for these indefinite integrals, you always need a plus c. The way you can tell, and I don't want to get into this too much now, but if there's no numbers here, and here, like on the integral, sometimes there's going to be numbers. If there's no numbers, you need a plus c on the end of your solution. So the constant of integration has to be on there. Okay, so this is the general rule. Increase the power by 1, divide by the new power, which can be frustrating at first because you've just done calculus 1 maybe, or you've done it at some point in the past, and you've learned to multiply by the power and reduce by 1. Now you're learning increase by 1 and divide by the new power. So it can be a little difficult. So if you find yourself getting frustrated and doing part differentiation, part integration is cool. That's totally normal. I've got students who do that all the time, so it will take a while to get used to the technique. So let's try and apply that technique to these different formats of example here. So starting with this one. So this is in the correct format. First of all, check the format. Is it in the correct format? These are all in the correct format. We're going to deal in the next class actually with formats that are not acceptable to use the power rule on. This is fine. So we increase the power by 1, which takes the x squared up to an x cubed. Divide by the new power. So divide by that new power, that 3. And that's you done. That is it. And then we just go plus c, just as a notational thing to add that on there every time. Just get used to adding that on. Why is that the integral? Because it's the antiderivative. In other words, if we differentiate that, multiply by the power, multiply by the 3 would cancel out that 3, take 1 off the power, it goes back down to a 2, and you would end up with that. So in other words, you can always check your solution by differentiating it. If you differentiate the integral, the thing you get here, you should go back to the thing you started with. That's always a check mechanism. Remember, I think 2 classes ago or something like that, the one where we defined integration and antiderivatives as being the same thing, we had a little graphic there where we said that you differentiate one way and you integrate the other way. That's exactly what I'm doing here. So we've integrated to go from here to here. You would then differentiate to go from here back to here. Okay, so moving on, next example. This is in a very straight up format. The a value here is essentially 1. So we're just increasing the power by 1, which goes up to an x to the power of 6, and then dividing by that new power and putting the plus c on the end. Just be aware that there might be times where you prefer, instead of writing it in this format, to pull the fraction in front, to write it as maybe 1/6 x to the power of 6 plus c, like that. And there's reasons for that, mainly because later on you're going to start evaluating these as numbers. You're going to be putting numbers in here. Personal preference comes into play. You might prefer to evaluate it in this way rather than this way. It's up to you, but just be aware that you've got those 2 options. Are both fine, both acceptable. Okay, looking at the next one. So again, in the correct format, so we can just go straight to our integration. So increasing the power by 1. So we've got 1/3 x to the power of 5. We then need to divide that by 5. Now, you could just say, well, that is just all over 5. And that's true, and that is correct, but it's a little messy. We've now got quite an ugly looking thing. So there's a few ways you could overcome this, but basically, we want to combine these two, right? We're basically saying 1/3 divided by 5. Well, if you divide a fraction by a whole number, you basically can just multiply the number to the bottom of the fraction. So it seems contradictory to be multiplying when you should be dividing, but if you multiply this number to the bottom of the fraction, you're making the overall thing smaller. So we've got the number 1/3. We want to divide it by 5. Well, you could divide it by 5 by dividing the top by 5, but 1 is not divisible by 5. So you could do that if that was a number like a 5 or a 10 or some multiple of 5. But the other way, the more convenient way in integration, you're going to see this a lot, is just to multiply the bottom of the fraction by 5. That does the same thing. Making the denominator of the fraction 5 times bigger makes the overall fraction 5 times smaller. That's what we wanted to do. We wanted to make 1/3 5 times smaller, divide it by 5. We can do that by making the denominator 5 times bigger. You'll see that often in integration, this sort of format here. You'll get used to it pretty quickly. So we could just take another line to write that as 1/15 x to the power of 5 plus c. And what you'll maybe find, as you start to get more comfortable with these formats, you probably will just skip this line here and go straight to that as your final answer. Okay, so the next thing would be a format where you've got multiple terms. So just like differentiation, it doesn't matter how many terms you've got, as long as they're all in the correct format to use the power rule, which they are, then you can go ahead and use the power rule. Or you can even combine rules. Later on we'll see scenarios where we might need to use a power rule here and then a chain rule here or something like that. Again, just like differentiation, you can combine rules there as well. So maybe a little bit trickier this one. We've got to increase the power by 1. So let's just think about that. We've got the number 2/3. We want to add 1 to that, so increase the power by 1. Well, that's just 2/3 plus what we can think of as 3 over 3, which becomes 5 over 3. So we know that the power is going to go up to 5 over 3. Okay, you'll see that a lot again when you've got a fractional power, you've got to add 1 to it. So you need to think of that 1 as being whatever the denominator of the fraction is over itself, with 3 over 3 in this case. So we end up with 2x to the 5 over 3, but we need to then divide by that new power. So we're dividing by 5 over 3. I'm just going to leave that one like that, and we're going to do another line of working. I'll come back to that in a moment. This one here, increase the power by 1, that goes up to a minus 1. If you're then dividing by minus 1, you're just basically making the plus 3 into a minus 3. So let me just show you that. So that would be x to the minus 1. We've got the 3 there. We're now dividing by that new power, which is minus 1. But if you divide 3 by minus 1, you just get minus 3. So all we need to do, we don't need to actually divide by anything. We just need to put a minus in there. And then we've got our plus c again on the end. So let's think a little bit more about this one. Essentially what we've got here is the number 2 being divided by 5 over 3. So that's 2 divided by the fraction 5 over 3. But you should know that dividing by a fraction, you can just turn it into a multiply and take the reciprocal. In other words, flip the fraction. So 2 times 3 over 5 is just the same thing. 2 times 3 over 5 is 6 over 5. So this becomes, where are we here? This becomes 6 over 5 x to the power of 5 over 3. A little bit messy. It will take you a while to get maybe used to those. It will start to show up how good you are with fractions quite quickly. There's quite a lot of fractions, unfortunately, in integration. They can be difficult to deal with, but you'll get used to them. Okay, so that one comes out to be like that. Okay, and then finally, let's look at this example where we've got just a constant. Now, in differentiation, when you differentiate a constant, you get 0. It's different in integration. In fact, let me just show you the answer and then we'll explain why. So the answer here is 7x plus c. Now, why is that? Well, I'm claiming that this here is the antiderivative, the integral. If that's true, then if we differentiate this, we should get back to this. And if you differentiate 7x, you do get 7. If you differentiate c, some number, some constant, you get 0. So differentiating all of this would give you that. So that is true by that definition of antiderivative. The other way you can think about it is that this is the integral of 7x to the power of 0, because x to the power of 0 is 1. So that's basically like 7 times 1. So it's a fancy way of rewriting 7x to the 0. Using our power rule on that, we would increase the power by 1. So we get 7x to the power of 1. We divide by that new power, so 7x to the 1 divided by 1 is just 7x to the 1. So we get 7x to the 1 plus c. Of course, we don't need the 1 power, so we just really get 7x plus c. But you don't need to go through all of this, that's just for demonstration. You just need to learn that when you integrate a constant, you get the constant in front of an x. So if it's 7, you'll get 7x. If it was 5, you get 5x. And you can always just check that or remember it by the fact that if you differentiate that, you would get back to that number there. So that's basically an explanation of the power rule. So this is the format you're looking for. This is the rule, increase the power by 1, divided by the new power. And these are a few of the scenarios you're going to see which you can apply the power rule to. There's going to be more scenarios. It's going to take you a while to get used to all of the different fiddly little bits you've got to do in the middle there with fractions and stuff like that. In the next class, we're going to consider integratable form. So we're going to consider formats of this part here, which are not ready to be integrated, and we have to manipulate them first. Just like we did in differential calculus. Things in differential calculus were not always ready to be differentiated. We had to manipulate them, usually by indices rules, to get them in a format like this, which were then differentiable. Same here in integration. So definitely check out some practice questions on the power rule. Super important as a foundation for the rest of Calculus 2. Once you're comfortable and happy with that technique, then you can move on to the next class, which is integratable form.